In this video, we'll explore the binomial distribution, one of the most useful kinds of probability distributions for real-world scenarios. Think about how often you store data on the cloud. It's become an indispensable way to have access to our data anywhere we go. But if those huge servers where your data is stored go down, that can be a serious problem. That's why companies make use of redundancy. The exact same data is stored on multiple servers. So if one goes down, you can still access your data on one of the others. We can model this situation with a random variable. Suppose a cloud computing startup has 4 servers, each of which has an 80% chance of being up and running at any given time. Yes, I know that's pretty low, but bear with me, it'll make the calculations easier. Let's use a random variable x to denote how many servers are up and running, and see if we can get a handle on the distribution of x. To start off with, what's the probability that all 4 servers are up, so x equals 4? Well, assuming all 4 servers are independent, which they usually are for something like this, then we can just multiply the probability that each one is up, 0.8 times 0.8 times 0.8 times 0.8, which gives an answer of just under 41%. Yikes. Should we be concerned? Not necessarily. Let's look at the probability that all 4 servers are down, so x equals 0. If there's an 80% chance that a server is up, then there's a 20% chance that it's down. So the chances that all 4 are down is 0.2 times 0.2 times 0.2 times 0.2, which comes out to 0.0016, not even 1%. And that means that there's a 99.84% chance that at least one server is up. That's the power of redundancy. Let's keep going with this scenario. What's the probability that there's exactly one server running out of the 4? Well, the probability that the first server works and the other 3 don't is 0.8 times 0.2 times 0.2 times 0.2, which comes out to 0.0064. But that's only one of 4 possibilities. Maybe it's the second server that's running, or the third, or the fourth. But in all cases, we get the same answer, since order doesn't matter for multiplication. So if we add up all of these possibilities, we get the overall probability that there's exactly one server running, any one server, which comes out to 2.56%. In fact, this suggests a more general way to calculate the probability that any number of servers is up. Multiply out the probabilities for the servers that are up by the probabilities for the servers that are down, and also multiply by the number of orders in which this could happen. In this case, 1 server being up and 3 servers being down can happen in any one of 4 different orders. If we keep going with this idea, we end up with the entire probability distribution for x, telling us exactly the probability that any number of servers is up and running at any given time. Try to work out these numbers for x equals 2 and x equals 3 on your own, by the way. The idea is largely the same as what we just did. This type of scenario is so common that it has its own name. It's called a binomial distribution. In a binomial distribution, you have a set number of trials, which we usually denote n, and they have to be independent. Also, those trials have to have exactly 2 outcomes. Usually you hear them called success and failure, though really these are just labels. Depending on your application, for example, you might define finding a defective part in a batch as success. The important thing is, if success happens with probability p, then failure must happen with probability 1 minus p. That's just the complement rule in action. So in our example, we had a binomial distribution with n equals 4, since there were 4 servers, and p was equal to 0.8, since there was an 80% chance that a given server was up and running. We can also write down a formula that sums up how to calculate the probability that we have some number of successes. Multiply the probabilities of all the successes, times the probabilities of all the failures, and finally times the number of orders in which those successes and failures could have happened. In practice, though, we usually use software to calculate these probabilities for us. Excel has a built-in function binom.dist to calculate binomial probabilities. Just enter in the number of successes you're looking for, then the total number of trials, and then the probability of success. Finally, the last entry is either a 0 or a 1. Use a 0 if you want the probability of a single value, or use a 1 if you want the cumulative probability up to a certain value. So, in our previous example, if we wanted to find the probability that x equals 2, that's binom.dist with 2 successes out of 4 trials, with a 0.8 probability of success, and a 0 at the end. That confirms the 15.36% chance that we saw earlier. If we change that last 0 to a 1, that'll tell us the probability that x is at most 2. That is, x equals 0 or 1 or 2. That cumulative option can save you a lot of time. Otherwise, you'd have to add up all those individual probabilities yourself. For some more practice, consider some tweaks to the problem we did earlier. What if n were 5 instead of 4? Or alternatively, what if p were 0.9 instead of 0.8? Think about what each of these changes would mean in the context of our real-life situation with the servers and cloud computing. And also think about what you'd do if you had a choice of making one upgrade versus the other.